Okay, here we go. So now we're going on to Newton's second law. Wow, that was like 45 minutes on the normal force. I didn't think that was possible. All right. Okay, Newton's second law answers the age-old question, what do forces do to an object? Okay, so N2, all right, because we're running out of time. A net force on an object causes it to accelerate. According to the famous equation. And don't forget the sum sign. That'll help you remember. It's the net force. It's not just any old force. The sum of the forces equals the mass times the acceleration. Okay. So you want to know what all the squiggles on that equation mean. This reminds you that it's all the forces. It's technically all the external forces, but let's not worry about that. So it's the net force is what the sum is reminding you of. It's the forces. This was the mass acceleration vector. Right? And that's it. Newton's second law. Pretty much all of mechanics is just that. Okay? It also answers that initial set of questions about what's the natural state of motion. The answer is constant velocity. Right? If anything is slowing down, if it's speeding up, it's because of a force, gravity. If it's slowing down, it's because of a force, friction. It wants to keep going in the same velocity unless it's acted on by a force. So now we know the ancient answer. Okay? So we're going to do a quick problem using this, because what do? Once you calculate the force, then you just do kinematics. Okay? So we'll do a quick kinematics problem just to show you what they look like. It's not a hard one. All right, or we'll do friction next time. Let's see. Okay, so the question is just how fast at the bottom for this situation. There's more to it than that. Let's see. So you have a mass sliding down a ramp, right? The ramp is at theta. The mass is here, like that. And it's going to go a distance d. And then what's v final? That's the quick drawing of the question. Okay. First, I would draw a free body diagram. Probably be the best thing to get started with. And the free body diagram, you're going to say, well, the gravity is straight down, mg, or weight, if you prefer. And the perpendicular, or the normal force from the ramp, is always perpendicular to the surface. So it's that way. We're not using our subscripts because we're only considering one normal force, but it's the normal force of the ramp on m. Okay, we'll use a subscript. Ramp on m. Okay? So now we do the kinematics. So now you can decide, is the normal force pushing it down the ramp? No. We should not do this. You could do this as a 2D kinematics problem, right? It's following this way, and it's following this way, and you can be all Cartesian about it. Don't. Right? This is one you want to rotate your coordinates and go down the ramp. Okay, so use the coordinate parallel to the ramp. It'd be the efficient way to do this problem. So you just apply Newton's law. You say sum of the forces down the ramp equals the mass times acceleration down the ramp. I'll use my little parallel symbol. That's all you got to do. Okay, so what are the forces down the ramp? Well, the normal force gives you no force down the ramp because by definition it's perpendicular to the ramp. So it's only gravity, mg. So if we want that component, we say, well, mg is made up of a component going into the ramp and along the ramp. All right? And this angle is this angle. Because if I brought this angle towards 0, this would tilt up and it would go towards 0. So it's that one, it's not that one. This one would go to 90 if I brought it towards 0. So then you just do your SOHCAHTOA and you say that's the opposite. Sine is opposite over hypotenuse because mg is the hypotenuse. There's the right triangle. So mg sine theta is the force down the ramp. All right? So we say mg sine theta. Is that a component or a magnitude? That's kind of vague, right? I haven't told you which way is positive yet, so you don't really know. See how it can be arbitrary about the negative signs? I'm going to tell you that this is positive down the ramp, positive parallel direction. Therefore, that's a magnitude. That's a component because it's going to be positive. Of course, I've defined theta negative because I drew it this way, so God knows, right? Technically, theta's in the negative theta direction, so a bunch of negatives are going to cancel. See, this is why we don't do the detailed every time. This is why we just look at it and say, okay, it's positive, it's down the ramp. I'm a pumpkin spice latte sipping basic whatever. I do it too. Equals mass times the acceleration down the ramp. Okay? And then we see the interesting thing about gravitational forces is that the mass goes away, right? Motion is, the accelerated motion depends on mass, but the gravitational force also depends on mass. It's almost like there's two masses. But why do they come out the same? We make them the same. Right? So that's the weird thing about mass. Let's not get into it. There's inertial mass and like quantity of matter mass. It goes away, and we find that the acceleration down the ramp is basically just g sine theta. Right? That's all you really need. And once you have that, then you do 1D kinematics. If you want to solve this now, hopefully from the last 2 weeks, you know exactly what to do. As you say, well, I'm accelerating. Am I accelerating for a distance or am I accelerating for a time? Well, both. Okay, am I accelerating? I've been given the distance or the time. You've been given the distance. And when you've been given the distance, you use the little shortcut formula where we combine two other formulas, where v final squared equals v initial squared, say we started from rest, plus 2a acceleration is g sine theta. And then d, we gave you the easy d, right, down the thing. Right, we're going to give you an easy d. Right. So it's just a square root of 2g sine theta d. V final is the square root of 2g d sine theta, and that's the answer. So there we kind of did it. It's almost, this comes up so often, it's almost worth memorizing. That if you have something on a ramp at an angle theta, the force down the ramp is mg sine theta. That's just so common in so many problems. You know, that might be worth just having quickly something you can recall, right? The acceleration will be g sine theta if there's not other forces on it. But mg sine theta is the force. All right. Oh, good Lord. 3 minutes. This is friction. I don't know what to. I don't know if I can do friction and tension in one lecture. Oh. Okay, we're done. I can't do friction.